Hello, my name is Andrew Cheek and I'm a postdoc at CP3 in UC Leuven in Belgium. This is my contribution to 2021 Week Interactions and Neutrinos workshop, and today I'm going to talk about a work I completed with these lovely people earlier this year about dark matter phenomenology from upcoming neutrino telescopes. And what we do in this work is we make sensitivity projections using a new type of analysis technique, and we explore the implications this would have on simple dark matter models. I want to mention that you won't have my floating head somewhere on the screen, and that's because I had some technical difficulties with getting the resolution right. So I've decided not to bother with the aim of making sure you can see everything as clearly as possible on my slides. So as we know, dark matter annihilation is central to thermal production, which is a possible mechanism which produces the correct relic abundance of dark matter that we observe today. And looking at a fairly recent review paper, you can see that neutrino experiments in general, for basically all the mass range of dark matter particles, do not probe this thermal relic abundance line. In this project, we were interested in this possibility of KM3NET, the cubic kilometer neutrino telescope that will be located in the Mediterranean, which sort of shows the potential to probe really deep into the parameter space, getting very close to the thermal relic line, and it's very interesting because this area of parameter space is fairly unprobed by neutrino telescopes. So in general, this is quite exciting because it's always exciting to probe physics in areas where we have previously not probed, I think there's other reasons to kind of be excited by this prospect, and that's because neutrinos have interesting kind of similarities or connections, possible connections with particle theories of dark sectors or extended theories with dark sectors. The kind of first order stuff that I just want to mention is the fact that neutrinos have similar characteristics to dark matter, i.e. their charges, and also the non-zero neutrino mass means means this is a good direction to observe or look for physics beyond the standard model. But also from a more practical point of view, neutrinos are just a great messenger particle for astrophysical sources, including dark matter. So this new analysis technique that I mentioned in the first slide uses the angular power spectrum, and it was originally developed to help differentiate dark matter, whether it decays or dark matter decays or annihilates, and astrophysical signals. Here I show some sky maps at the bottom, and basically what I'm showing here is how the different signals are distributed on the sky. Astrophysical background on the left is nearly isotropic, and it contains the atmospheric neutrino background as well as astrophysical components that are described by a power law. In the middle and on the right, I show decaying and annihilating dark matter, and these are highly correlated with the position of the galactic center on the sky, and therefore anisotropic. Previously, the collaborators on this work, in their previous work in 2020, they took KM3NET and made the sensitivity projections for values of dark matter going down to 200 TeV. We extend this in our paper by pushing that lower limit further down to 200 GeV. I just wanted to sort of overview a little bit on how we do this analysis. And basically what we do is we simulate neutrino sky maps that KM3NET will observe, and then we expand the sky map on spherical harmonics. And we build up a power spectrum in the usual way by taking the average expansion coefficient over the sky, defined here. And then since dark matter signal, the signal that we're interested in is anisotropic, we look for anisotropies on the sky. We get rid of the monopole contribution, and we normalize by the total number of counts, neutrino counts, and then we can build a chi-squared from the average expansion coefficients from the mean over our data set, or our data set of simulations, and the covariance matrix, which is also taken from the data set of simulations. This chi-squared allows us to build a PDF which allows us to define a p-value and then get the respective limit. Okay, so that's all well and good, but another reason why we actually do this, other than simply to be a potential way of determining determining whether this is dark matter signal or a astrophysical signal, is that when you look at studies which constrain dark matter signal from the galactic center, often you find that the uncertainty we have in the dark matter profile in our galaxy, especially in the inner regions, as shown here, is so profound that it can actually prove to change the constraints that we interpret in the particle physics by a substantial amount. Here I show the Antares limits, exclusion limits, which are affected by about an order of magnitude, just over an order of magnitude, depending on which dark matter halo profile you take. So one of the things we wanted to do with this APS, this annual power spectrum study, was to look at whether this analysis technique can help reduce those uncertainties. And indeed, when we perform our projections assuming 10 years of data taking, we see that this method is quite robust to the changes of dark matter distribution. We see here the blue solid line is our NFW profile, and our dashed dotted line is the Burckhardt profile. We show these big regions here, which is basically the Antares and ice cube limits, using the standard method, where you have a higher degree of difference from depending on the halo profile that you pick. And then we compare also to the other APS study that was performed by IceCube, and we obviously see that we predict that KM3net will be able to get a sensitivity sort of over an order of magnitude stronger. Okay, so now once you have your model independent bounds, it's important to kind of think about possible particle physics models that our telescope would be uniquely able to probe. And so our aim in this study was to be as simple as possible, hopefully only having one dark matter particle field and one portal field. And a good starting place for that is this paper from 2017, where they catalogue lots of simple models with one dark matter candidate, and usually with one portal, but not always the case. Generically, what they see is that they always have to deal with a charged lepton sort of channel, and therefore you'll be also constrained by gamma ray telescopes. This is simply because the neutrinos live in the SU2 lepton doublet, so you can't easily sort of separate out the two the charged leptons from the neutrinos. In this plot here, we show a specific we show the same limit from before, but now assuming the 50% branching ratio between charged leptons and neutrinos, and then also we show the Fermi-Lat constraints that we'll be considering in this paper. So we decided to stick with the Fermi-Lat toroidal constraints, basically because the astrophysical uncertainties affect the limits less than, say, the Hess galactic center constraints. Alternatively, we could have, but we didn't, look into the neutrino portal to dark matter, and this is where you have the dark matter, some kind of mediator like a scalar or a vector, and additionally a sterile neutrino. And this can give you clean, like 100% branching ratios or branching fractions of annihilation into neutrinos. However, because of the limits on the heavy active neutrino mixin, it makes it quite difficult to get a dark matter mass above approximately 100 GeV, which is still perturbative. And this is essentially the region of parameter space where we are most interested in, given that our K-free limits start at 200 GeV. So we decided not to go down this route and stick with just the one portal, one dark matter candidate. Another thing which sometimes is missed in the literature is the dark matter direct detection experiments, like the one in this schematic, are often really quite constraining. These experiments use, well, in the mass range of like a few hundred GeV, the most constraining experiments are the likes of xenon 1 ton, where they consist of xenon atoms waiting to be recoiled by some kind of diffuse dark matter component. And sort of naively, leptophilic models don't interact with these experiments because they don't have tree-level interactions with quarks and gluons, but at the loop level and with radiative corrections, these leptophilic models will be constrained at low energies and to a substantial degree. For example, when you look at the parameter space of a simple like scalar mediated model, you get limits from xenon 1 ton which far outweigh Fermi lap, but also are in excess of the sort of projections that we have for K and freenet. This is partly because with K and freenet we want our dark matter mass to be as high as possible, and in this scalar model, the cross section, it's a T-channel diagram, and you basically have this behavior where the mass goes something like 1 over m squared, where the mediator mass also has to be heavier than the dark matter mass. So your cross section is suppressed as you get to higher dark matter masses. The way you can kind of reduce this suppression as best you can is by having a small mass splitting, which is what we show here in this plot on the right. But even then, when we go down to small enough mass splittings, even with the case where we take our coupling to be at the perturbative limit, xenon 1 ton is still very, very competitive, even with our future K and freenet projections. In this blue band here, we basically are showing the uncertainties associated with having a with the local dark matter density. We don't show this in future plots, but we just wanted to outline it here. In the black as well, we have the Fermi lat constraints, and the black dotted line is where you'd expect the thermal relic line to be if it's just a simple wind sort of early universe scenario. Okay, so that's the scalar mediated model, but what happens with the vector mediated model? So here we have a Dirac fermion and a vector mediator, which couples our dark matter to our standard model leptons. And in this case, we have an S-channel diagram which dictates the annihilation channel. And here you can typically, well, here you can enhance the cross section by sitting on the resonance. So this is why you have this funnel shape, and then you can have cross sections which are fairly high for higher masses. And this is borne out here where we see that K and freenet, our projections for K and freenet will push past Fermi lat constraints and also the xenon 1 ton constraints. Now, in these plots here, I'm showing a specific coupling configuration where the new vector boson couples only to the standard model a left-handed doublet, and that is basically to preferentially sort of, or give us the best shot in the neutrino sector, basically by setting the branching ratios to be 50-50. However, as many of you may know, this coupling structure has problems. Having a non-zero axial vector violates perturbative unitarity at high energies. And this happens, in the standard model with the weak bosons, and analogously, you can fix the problem by introducing a new scalar, like what the Higgs does in the standard model. But then when you add this new scalar, then you have more experimental constraints to deal with, and also we're no longer in a situation where we're looking at a simple model. So instead of doing that, we decided to abandon this and look for models which are on a stronger theoretical groundwork without adding too many new particles. So when you do that, one thing you have to keep in mind is having anomaly-free models where you take your new U1 gauge field and you look at the anomaly which comes from the triangle diagram, where all your new fermions in your field also run through, or your standard model fermions run through this loop. The simplest anomaly-free U1 extension in the standard model is the L alpha minus L beta model, where alpha and beta are the generations of the leptons, where the weakest example of such, or the one with the weakest experimental constraints, is the one called the L mu minus L tau, and this is basically because you can avoid constraints coming from electron couplings with your new vector, and also adding additional vector-like fermions that couple to this U1 gauge boson doesn't introduce any anomalies as well. So that will be useful for our dark matter model. So we can play the same game as we did before, but now we have a model which is on sturdier theoretical ground. And also in pink, I overlay on the right here this interesting region where you can have this new boson connecting with the flavor anomalies that you observe in your LHCb. The scale of this boson has to be small enough to have a measurable effect at LHCb, so that's why it stops off here to the right. And it's important to note that in order to actually have this model address flavor anomalies, you have to add new physics, but it can be sufficiently above the dark matter scale that it doesn't affect the findings here. The L mu minus L tau model has been associated with another fashionable hint of new physics for much longer, and that's of course the tension between experiment and theoretical prediction for the muon anomalous magnetic moment. Tantalizingly, the simple extension of the standard model can explain the current tension if the new boson has a mass of around a couple of MeVs to hundreds of MeVs. If you want more information about that, I send you to Dorian Amaral's Asynchronous talk. But for our purposes with K and Freenet, we want our dark matter particle. We want a dark matter particle, which isn't necessarily on this picture on the right, and we want it to be above 200 GeV. Now, in this situation, dark matter, this model will be severely constrained by direct detection, now more so than previously because we're no longer suppressed by the mass of the mediator because it's now light. So if we want to consider these light mediators, we have to go to a secluded regime where the coupling to the standard model or to the muons and the tauons is much less than the coupling to the dark sector. So this basically introduces a dominance of the diboson channel in annihilation. So this is our new Z. And also it's a legitimate question to ask whether you can go to sort of infinitely low couplings to the standard model to avoid direct detection. And the answer is no. The Big Bang nuclear synthesis constraints mean that the lifetime of your mediator needs to be less than 1 second or shorter than 1 second. But we found that the constraints from Xenon 1 ton and LZ, so Xenon 1 ton, the existing bounds are around here, just above 10 to the minus 8, and LZ will be able to probe sort of a region which is just below 10 to the minus 8. But still, we've got quite a large region of parameter space to play with, so we can always choose the coupling between the new boson and the standard model to be small enough to avoid direct detection constraints. There are other interesting sort of aspects, though, of particle physics or particle physics phenomenology that come when you consider this secluded model. And most importantly, I think, for the KM3net bounds or KM3net probe, is that in the case where your mediator is now smaller than twice the mass, the mediator mass is now smaller than twice the mass of the muon, your branching ratio to neutrinos is 100%. So this is exactly what you kind of want for KM3net. Additionally, in this regime where the mediator is much lighter than the dark matter particle, Sommerfeld effects can play an important role. Sommerfeld effects basically are the non-perturbative sort of phenomena where incoming particles can exchange an infinite ladder or a tower of their light particles, of a light mediator. And this can affect or enhances things like annihilation and self-interaction. So this enhancement goes like 1 over v squared, and now that means that the CMB is much more constraining than our Fermi constraints earlier. So now what I have to do is I have to show Planck results which constrain dark matter annihilation in the CMB. Still, though, we have this really interesting region of parameter space where KM3net is projected to be the most sensitive to, and it also overlaps with the possibility of a new light fermion relieving the Hubble tension. So in conclusion, we provide projections of a KM3net-like telescope with a new angular power spectrum technique, and this APS allows you to minimize sort of uncertainties when it comes to the galactic dark matter density. We explored some simple models for dark matter and saw how this analysis will fit in with the experimental landscape once it happens. But we also highlighted interesting possibility for the secluded U1 L mu minus L tau model, in which KM3net will be sort of uniquely poised to make interesting statements about. So with that, I say thanks for listening, and I'll see you at the panel session.